So today I'm going to be talking about a little bit about my work on microplastic ingestion in mussels and what this means for us as humans, but more importantly, the significance of this for ecosystem conservation. And near to the end of my talk, I'm going to allude to how we can use this data to maybe start looking at biomonitoring protocols using mussels as bioindicators of microplastic pollution. So mussels aren't really very visually stimulating. They're actually quite boring, but they're very ecologically important. And this is because they are a food source for a wide number of marine animals. They also help with water purification by their filtering mechanisms. And also they encourage species diversities because the mussel beds allow or are a habitat for other marine invertebrates. But besides the ecological significance, some people actually like to eat mussels, especially if they're cooked, in like a creamy white wine sauce. That sounds horrid, but it's each to their own. But these tasty intertidal treats are not just enjoyed by seafood connoisseurs, but are also relied upon by a large local subsistence sector as their main source of protein. And the problem with eating mussels is that if you don't cook them properly, you'll probably get food poisoning. And this is because they accumulate toxicants from the marine environment into their flesh. And this has been quite well studied for heavy metals and persistent organic pollutants and how these actually affect the mussels. In fact, these accumulating properties of the mussels are actually using something called a mussel watch program, which uses mussels to detect and monitor levels of heavy metal pollution along the South African coastline. And while we know very much about heavy metals and POPs and what they have to do with mussels, what we do know very, very little about is the huge problem of mussels also ingesting tiny pieces of plastic called microplastics. Deborah's already given us a little bit of introduction, but a microplastic is any plastic particle smaller than 5 millimeters in size, and these are primarily manufactured for use in cosmetic products as exfoliants. A secondary source of microplastics actually is from the breakdown of larger plastic items in the marine environment. A more interesting note, your washing machine at home is also a source of microplastics. Because most of our clothes nowadays are made of synthetic polymer materials, as they are spun around in the washing machine, the drum actually acts as a grater, which strips microfibers off, and these are washed into waterways and eventually into the marine environment. The important question is, does size matter with microplastics? It does. 5 millimeters in size, it's a quite small measurement, but relatively large when we think about how many microplastics have been found in the marine environment down to the micro and even to the nanometer scales. Plastics and microplastics accumulate in the marine environment and will continue to do so as long as plastics are being produced. And we're all quite well acquainted with the problem of bigger plastic particles and how these affect the larger marine animals. Well, what about microplastics? I've already said they're so small, but if they're so small, why is it a problem? But that's exactly the problem. Because they are so small, they become available to ingestion by marine organisms. And once this happens, this may lead to gut damage and blockage of the organism who eats the microplastics. And because microplastics have absolutely no nutritional value, the animal becomes malnourished, which leads to reduced survival and reproductive fitness. An additional, perhaps more worrying problem is the fact that microplastics act as almost a magnet, and they attract pollutants in the marine environment onto their surface. And once an animal ingests these plastics, these pollutants may be transferred to the flesh of the organism, leading to trophic transfer and perhaps bioaccumulation up the food web. But not all marine animals are equally at risk of microplastic ingestion. It's actually the filter feeders, such as mussels. And this is because they are non-selective. This is a bit different to the traditional train of thought. It's usually been said that mussels can actually taste, for lack of a better word, between non-nutritional items and between their food. In the beginning of my honours year, my supervisors were also convinced of this and convinced me as a fledgling biologist that I need to dedicate my time and effort during my honours project to investigate this. As you probably guessed, it was an absolutely spectacular failure because the mussels ate everything, all the plastics, all the food. And we probably should have looked at the literature a little bit more in depth, because that has actually been shown in previous studies before mine. And if you look at the picture on your left-hand side, that is actually one of our mussels. It's under UV lights, and the circle is showing you the plastics that it's eaten. And while we know that now mussels eat microplastics, we still know very little about how these plastics affect the mussel's physiology. So what we looked at was physiological changes, which are actually, you can use them as determining stress of the mussel, and we looked at these changes of perna, which is quite a dominant mussel along the KZN coastline. We exposed them to various microfiber concentrations, and the two things we looked at was, one, their filtration rates over 1 hour, and two, their feeding over 24 hours. But in order to do this, we had to make our own microplastics to make sure that the sizes, the composition of the polymers, and the shape were all the same throughout our treatments. So it was a very basic but very, very tedious process. Pretty much we took a safety jacket, which is made of polyester, and we cut it into tiny, tiny pieces and cut it even more to make almost a fluff. We mixed this in some ethanol and filtered them between 100 and 10 micrometers in size, and did that over and over and over again until we had the desired quantity that we needed. So just briefly looking into our methods, to look at filtration rates of mussels, we use live and dead mussels. And I don't know if you can see in this very poor quality video clip that I made, I'm sorry. We use live mussels because they actually filter the water, and dead mussels obviously don't. But we use the dead mussels as a correction factor for settling of the microplastics, and also the microplastics sticking onto the actual mussels. And what we did, we exposed these mussels to concentrations of microfibers at 1, 2, and 5 milligrams per liter, and simply took water samples before and after 1 hour, filtered them, and used UV light microscopy to count them. And this is just quickly what we got from this. So on your x-axis, you can see the different microplastic concentrations and the filtration rates on the y-axis. And what this graph, the main point that this graph is showing you, that mussels exposed to higher concentrations of microplastics had significantly suppressed rates of filtration than those exposed to the lower concentrations. Quickly moving on to the feeding methods. We use the same concentrations of microplastics, but this time we left the mussels for 24 hours to feed. After this, we dissected out their guts. We used a digestion process using sodium hydroxide, and we filtered this again using UV light microscopy to count the number of particles. And interestingly enough, this graph shows the opposite trend of the previous one, where in 24 hours, the more plastics that the mussels were exposed to, the more they actually ate. And just to quickly sum that up, the initial filtration rates of the mussels was significantly suppressed in 1 hour, but the mussels almost adapted within 24 hours and were able to cope with the highest concentration tested. This means that mussels actually may be able to filter more microplastics in natural systems. And this increased ingestion of microplastics may potentially lead to increased transfer of heavy metals and persistent organic pollutants to the mussel. And this is all, we really need to know from this. What should we know? What can we gather from this? Well, 1, mussels passively ingest plastic. 2, the more microplastics in the marine environment, the more the mussels will eat. 3, microplastic ingestion by mussels negatively impacts their physiology, and this may have, as in all ecosystems, potential knock-on effects. The problem with microplastics is that we can't stop their inputs into the marine environment. We also can't remove them from the marine environment. But one of the available options we do have is to actually monitor the microplastic pollution and extent. But this already comes with its own problems. Because microplastic pollution is such a new field of research, there are no standardized methods for this. And also, it's limited by equipment. For example, if you are looking at a net trawl in a water column, any microplastics smaller than the mesh size you use won't be sampled and will be underreported, obviously. Because there's no standardized methods, many different people use many different methods. And this doesn't allow us to accurately compare microplastic abundances between studies. But based on the premise of what we know about mussels being able to eat microplastics, we're currently investigating the potential of using these mussels as bioindicators of microplastic pollution along our shorelines. So this would be based on the principles of the Mussel Watch program and the advantages of using mussels instead of the traditional monitoring techniques is that they are sedentary and available all year round, meaning that we're actually able to track microplastic pollution trends over both time and space. But more importantly, it will allow us to determine what is bioavailable to the mussels, meaning which microplastics the mussels are more likely to eat and which may pose the biggest threats on the mussels. So just quickly, in conclusion, just because we have very little knowledge about microplastic pollution does not mean it's not a real threat. And although our study focuses on mussels, microplastic ingestion has been shown in fish, zooplankton, sea urchins, copepods, meaning that microplastics are actually entering the food web in more than one way. But what about the people? Because mussels are such an important food source for so many people, this data highlights how microplastics may actually impact human food sources and really emphasizes the need for further investigations into toxicant transfer mechanisms. Obviously, we really need to figure out, which is what we're trying to do, an accurate monitoring system. And this will allow us to determine the actual distribution of microplastic pollution as well as fate and impacts, which will have major applicability in marine conservation in South Africa. Of course, no person is an island, and I couldn't do this by myself, so I'd like to thank my colleagues from MACE Lab, the NRF for funding, as well as the University of KwaZulu-Natal. Thank you.